Right, so section 1111 is applications of Taylor polynomials. Okay, now out of all the lectures that I'm going to upload for this class, this one may be the most useless. So all I'm going to do is just introduce a definition, and then that's pretty much the whole section. So here's the idea. Definition. Let f be a function that is real analytic, or in other words, that can be represented by a power series centered at A over some interval of convergence. Okay. Given a non-negative integer, let's call it k, the kth the kth degree Taylor polynomial of f at A, so long name for a very silly concept, is tk. This is the polynomial sum from n equals 0 up to k of nth derivative of f evaluated at A divided by n factorial x minus a to the nth power. Okay. Now, this is just the kth partial sum. Well, I don't know if I should call it kth partial sum because it actually has k plus 1 terms, but it's just one of the partial sums of the Taylor series. Yeah, that's it. That's the whole lecture. The point of these things is that they are a generalization of linearization, which you learned about in Calculus 1. Remember when you had a function and you wanted to find a line that approximated the function near a certain point? That was called the linearization. And what it did was it just found the line which best approximates the function at some point. This is a generalization of that in the sense that if k is 1, then this is the linearization. If k is 2, then this is the quadratic Taylor polynomial, which is just the best quadratic function that can be used to approximate your function. If k is 3, this is the cubic Taylor polynomial, which is the best cubic polynomial that can approximate your function at the given point, and so on. Okay? So yeah, you just take the Taylor series and then forget about infinitely many of the terms. That's it. That's the Taylor polynomial. So I probably don't even need to do any examples, but I'm going to anyway. Oh, and one more thing. Well, yeah, let me mention this later. So So example. Find the fourth degree Taylor polynomial of f of x equals e to the x at 1. Okay. Now, this requires that you just take the first 5 terms of the Taylor series. In the last lecture, we mentioned that the Taylor series of this function is sum from n equals 0 to infinity of 1 over n factorial times x to the... Wait a second. I've made a mistake in my notes. Okay, sorry about that. What we actually want here is the Taylor polynomial at 0. Anyway, as I was saying, that is, if you were to take the Taylor series centered at 0, that would be the sum from n equals 0 to infinity of 1 over n factorial x to the n, right? It's the first example that we did last time. Okay? So the fourth degree Taylor polynomial is, instead of taking the sum from n equals 0 to infinity, you just take the sum from n equals 0 to 4. That's it. And you can write this out. You know, this ends up being, let's see, 1 over 0 factorial times x to the 0, so that's 1, plus 1 over 1 factorial x to the 1, so that's x, plus 1 over 2 factorial x to the 2, so that's 1/2 x squared, plus 1 over 3 factorial x to the 3, so that's 1/6 x cubed, plus 1 over 4 factorial x to the 4th, so that becomes 1 over 24 x to the 4th power. And yeah, that's it. That's the fourth degree Taylor polynomial of e to the x at 0. Pretty lame, huh? It's just the Taylor series, but you forget about infinitely many terms. So, like I was saying, this is the quartic polynomial, the degree 4 polynomial, that most accurately approximates e to the x near 0. Okay? So, I said when we were talking about the theorem on approximating the sum of an alternating series that an approximation is useless unless you know how accurate it is. And I stand by that. Indeed, if you're trying to approximate a function by a Taylor polynomial, you better know how accurate it is, or else you're not going to know whether it's actually suitable for your purposes or not. And so there is an entire process of figuring out how accurate a Taylor polynomial is in terms of using it in place of your function. Okay, so like we could come up with a bound on the error in taking this function as opposed to that one, if we were doing some kind of application. That's that exists. That's real, and it's important. But it's not part of this class. If you're interested, it's in the textbook. It's in sections 11.10 and 11.11. But we won't need to discuss it for this particular class. All we're going to do is just find these Taylor polynomials. We don't actually need to discuss how accurate they are as approximations. Okay, so that's e to the x. Okay, now let's do another example. So now I want the second degree, so quadratic, the second degree Taylor polynomial of f of x equals the cube root of x at 8. Okay. So what we need to do is just take the Taylor series and then cut off all the terms after n equals 2. That's it. So in order to do that, we're going to need at least 2 derivatives. So first of all, the 0th derivative of f is just x to the 1/3 power. Evaluate that at 8, and what you get is 2. The first derivative is 1/3 x to the negative 2/3. You evaluate that at 8, and what you get is, let's see, 1/12? Let me make sure that's right. Yeah, 1/12. And then the second derivative, that's going to be negative 2/9 x to the negative 5/3. You evaluate that at 8. And what you get there is, let's see here. Well, I did it in my notes. Negative 1/144. Okay? And that's all we need. That's all we need. I mean, it's not enough to construct a Taylor series, but we don't need the Taylor series. We just need the second degree Taylor polynomial. Okay? So all we need here is the sum from n equals 0 to 2 of the nth derivative evaluated at 8 divided by n factorial x minus 8 raised to the nth power. And so in our case, that's just going to be 2 divided by 0 factorial x minus 8 to the 0, so that just makes 2. Then 1/12 divided by 2 factorial, so that's 1/24, x minus 8 to the 1, so 1/24 x minus 8 to the 1. And then finally, negative 1/144 divided by 2 wait. No, I messed that up. This is n equals 1 term, so we should actually be dividing by 1 factorial. So 1/12 divided by 1 factorial is actually 1/12. Sorry about that. Okay, now you're going to want to divide this by 2 factorial. That's going to give you negative 1/288. And then you have x minus 8 raised to the second. Anyway, that is the second degree Taylor polynomial of the cube root of x at 8. And let's do one more. So now we want to find, let's see here, the third degree Taylor polynomial of f of x equals e to the negative x sine x at 0. Okay. Now, finding the Taylor series of this thing would be complicated because every time you take its derivative, you're going to have to do the product rule. So, this is probably a little bit too hard for me to ask you to find its Taylor series. Well, it's not that it's too hard, it's just it would take too long. But if you want to find just its third degree Taylor polynomial, then you know for sure that you only need 3 derivatives of this thing. Okay? And so the 0th derivative, 0th derivative is going to be e to the negative x sine x. You evaluate this at 0, and what you get is 0. First derivative, that's the product rule, but you know, when you eventually do it, it works out to be e to the negative x times cosine x minus sine x. You evaluate this at 0. What you get is 1. Second derivative, this is negative 2 e to the negative x cosine x. Evaluate that at 0, and you're going to get negative 2. And then third derivative, this comes out to be 2e to the negative x cosine x plus sine x. You evaluate this at 0, and you just get 2. All right? So our third degree Taylor polynomial of e to the negative x sine x is the sum from n equals 0 up to 3 of the nth derivative, evaluated at 0, divided by n factorial, x to the n. This turns out to be, let's see here, 0 term is 0. One term is 1 over 1 factorial x to the 1, which is just x. Two term is negative 2 over 2 factorial x to the 2, so that's just going to be negative x squared. And then the 3 term is going to be plus 2 over 3 factorial x to the 3, and so that just turns into 1/3 x to the 3. And that's it. So this is the cubic polynomial that best approximates this function near 0. Okay? That's it. That's the whole lecture. Yeah, so hopefully you can see that this is pretty lame, right? It's just taking the Taylor series and just forgetting about the last infinitely many terms. And that's all. So homework is up. I guess you can get some practice with that if you need it.